The talk will be today about the interface between atoms and photons on a solid state system, and this is important topic because of fundamental interest to basically create such a hybrid system between atoms and photons, but also in terms of quantum information and quantum communication challenges, basically making quantum repeaters or distributing entanglement over long distances, where you use long-living state of atoms, long-living spin state, for example, and you distribute entanglement over distance by mapping the quantum state of the atom into state of the photon that propagates to the next atom, and basically that's create your long-range interaction. Now, the challenge to create such an interface where you have an efficient mapping of the state of the photon into state of the atom is considered to be as an important experimental challenge by many communities. And so nowadays there is quite a progress in making such devices using neutral atoms, ions, place it in a very high quality optical resonators, but also in a solid state system, so in a solid state emitters. And so among solid state system, I would like to highlight to you a few materials where you can find defects, optical color centers that are sort of similar to that atomic system X qubits, so relatively homogeneous emitters, and those are defects in the wide bandgap semiconductors like silicon carbide that host many color centers, while rare earths in silicate crystals, or defects, color centers in diamonds. So and today I'm going to talk mostly about diamond color centers. That will be my kind of atoms, artificial atoms that will be used as the active points in this light matter quantum interface. So what are the color centers, what they are so attractive? So diamond is a wide bandgap material, so don't have a color, but you might introduce defects that absorb and emit the light, and so this is a picture of the diamond that was doped very lightly on a part per million level, so 1 part per million of impurities, and these impurities are so-called nitrogen-vacancy centers. So this is a defect that is well studied now. So its atomic structure is well known. It's a nitrogen in a lattice position plus vacancy nearby. So this defect is is interesting in several respects. It has a strong optical absorption and emission, but it also can be created on demand in an ultra-pure diamond. Here you see a lattice of nitrogen vacancy defects created in a diamond by implanting one by one nitrogen ions. It's well understood and have also quite an interesting optical and spin properties. So first of all, about optical transitions. So what I show here is a G2 function of light emitted by this single defect. If you collect the light from every single dots in this implantation patterns, you see that the light exhibits a non-classical character in sense of anti-bunching, so at zero delay time, photons emitted by a single atom are always separated. That's just the signature of the single atom, but what you also see that there is some oscillations. Those are Rabi oscillations that your laser that is driving two-level system, the atom can be considered to be two-level system with ground and excited state. It drives it and induces several Rabi flops that you also see in the correlation function of emitted light. The decay time of this correlation function or oscillation in the correlation function give you optical coherence in the optical transition, and that's about 10 nanoseconds here, and 10 nanoseconds pretty long for solid state system. And it's also interesting that it's approximately correspond to decay of the excited state. So this emission here, or this absorption, is sort of a Fourier transform limited. So the photons that are now kind of getting here into play are not so much broadened by the environment. So this is important property of this as an element of such an interface. Now, yeah.
So it means that these oscillations are going to depend on the exciting power?
Yes, they are doing. So the oscillation will go like a square root of power. So the optical transition, and this is another important kind of property of these color centers, is coupled to the long-living ground state spin sublevels. So in V center have 3 spin sublevels in the spin 1 system, and you can control the spin state by optical pumping. You can rotate the spin by applying resonant microwaves, and the coherence time of the spin state is quite long, so even in ambient condition it can reach a few hundreds of microseconds. At low temperature it goes up to seconds, so the system is very well decoupled. So diamond is a magnetically non-active material. Carbon isotopes composing diamonds are not carrying any nuclear spin, so your atom is now sitting in a diamond lattice is pretty much isolated from environment in sense of magnetic interactions. So diamond can be considered as a magnetic vacuum in this respect, and that's why these defects show pretty long coherence time, at least for solid state system. You can also basically read out the spin state by measuring the scattering of photon, and that's created quite an interest in the system in many aspects of quantum information, quantum communication, but also in sensing. For example, there was a recent demonstration of long-distance entanglement between defects by Ronald Hansen group in Delft, and so this is basically show that also solid-state system can be brought in a good, well-controlled situation where they can be used as a node of such quantum repeaters, despite the disorder always present in a diamond lattice. However, I have to say that these experiments are still very tough and often require very long measurements. So distribution of entanglement is not very efficient yet, and some pre and post selection of color centers. So there are some challenges still associated with the solid state system, and I would like to discuss it today, and also the ways how to overcome them. So what are the typical challenges that have been discussed already today? What you find in solid state different from atomic systems. So in atomic systems, all atoms are the same frequency. In a solid state system, you usually have some strain in a material, some local electric fields, and these electric fields create you a stark shift on your, so atoms get shifted in the resonance frequency. They talk to photons at different frequencies, and that's why they're kind of not very interested or not very suitable for making connection over long distances, because they couple to different sort of frequency mode of light. So here's an example of this. This is a spectrum of fluorescence spectrum of area of diamond containing 2 different color centers, and because of this strain distribution, the different color center have slightly different frequencies. So you have on the left side color center that experiences low electric field. This one is a stronger electric field, and so these shifts can be quite significant. So there are many line widths, and that means that essentially these two atoms will not talk to each other. There is another challenge associated with NV color center, and it's its particular kind of signature that is making it difficult to bring it into this strong coupling regime between optical and atomic sides. So this is coupling to phonons. So our atoms are sitting in solid state lattice, and usually in fluorescence spectrum you have 2 parts. So emission of the atom have 2 parts, so-called zero phonon line, and it's actually for NV center pretty weak feature. So it's about 4% of emission is associated with zero phonon line. So, and this is the photons that are basically not getting any imprint of its quantum state in a diamond lattice, so that can be used for long-distance quantum communication, and very strong phonon sideband. So this is emission of the photon by atom with excitation of a lattice vibrations, and those are not very useful in this business. Now, so it's all the experiments so far in a kind of in the context of quantum optics with NV centers in diamond have been using this very weak part of the emission spectrum, zero phonon line, and that's why often those experiments are very, very slow. So you need kind of post-select very rare events, and so this is essentially a challenge when you think about scaling the system up or making this communication channel between distant atoms faster. This particular challenge, however, is related to intrinsic properties of NV centers, and today I'm going to talk about designing color centers in diamond with different properties and different structures that allow you to overcome certain challenges, associated still with this solid-state imprint. And so this is work in collaboration with a group of Mikhail Lukin in Harvard, Viktor Palyanov in Novosibirsk, Takayuki Iwasaki, Mitsuki Hatana at Tokyo Institute of Technology, Junichi Zhou at National Institute of Material Science in Japan, Valery Davidov in Troitsk, Phil Hammer in Texas A&M, and Alexander Kubanik in Ulm. So the design of new defects in solids will be about making structure more symmetric compared to NV center in diamond. Remember, nitrogen-vacancy center is a nitrogen sitting at a lattice position and vacancy nearby. So if you take a larger atom, it will not fit very well to carbon location. It will start to get shifted and will sit between two vacancies, and that's happened for silicon and germanium atomic impurities in diamond. So if you try to incorporate silicon or germanium in diamond lattice, your silicon, which is larger than carbon, significantly larger, will start to shift towards a vacancy, leaving a vacancy behind, and the structure essentially is an impurity atom sitting between two vacancies. It has an inversion symmetry, and it has a consequence on its spectrum. So because the atom does not possess any permanent electric dipole moments, the Stark shift for this system is only second order effect. So the small fluctuations or small variations of the electric fields at the location of individual atoms in a solid state will not lead to any spectral shifts, and we expect that these atoms will be much more spectrally homogeneous. So here is another interesting feature. So I mentioned before that NV center in diamond have this very strong phonon sideband. So because of high symmetry, silicon-vacancy center also very weakly couples to phonons. So here is a spectrum of silicon-vacancy center with very strong zero phonon line. About 70% of emission is in the zero phonon line, and about 30% only is in a phonon sideband. So this is now like more atomic-like system, much weaker coupled to phonons, but also much weaker get affected by the local electric field. Just maybe one point about spectral stability. So this system is because the atoms are much less affected by any fluctuations in the lattice, the spectral stability also getting remarkable. So if you measure the center of the emission of this color center as a function of time, so this is basically how stable is a spectral line, we can see that the atom sits within a megahertz, its accuracy of our measurements of a very long time, so about 8 hours acquisition time. So every individual atom is very, very spectrally stable. And if you will also look on many atoms, so they actually have a roughly identical emission spectrum. So here's a picture. This is a way how I'd like to show it. It's a picture of the diamond where every dot here is individual color center, and the color of the dot represent emission frequency. So the dots that have the same color essentially overlap in the emission spectrum within the line width. So the photons emitted by these different atoms, carrying the same color in this picture, are indistinguishable. So they overlap within about 100 megahertz for this particular color center. It's a homogeneous line width. And so if you start to take the photons, so extract photons from different color centers, so now different emitters in diamond, and bring them on a beam splitter, because they're indistinguishable, they will start to interfere. So you can think about following experiments. So you build an interferometer, Mach-Zehnder interferometer, where two input ports are two different color centers, and you extract the photons from two different color centers, and bring this on a beam splitter. And because the photons are indistinguishable, they will basically start to positively or negatively interfere, leading to no output events in a dark port of the interferometer, or all the photons are coming on a no events on a dark port. All photons are coming in a bright port. So in this case, the coincidence rate of photodetectors place it in a dark and a bright port of the Mach-Zehnder interferometer will drop to 0. So for indistinguishable photons, you expect no coincidence rate. So very kind of clear signature of indistinguishability of emitted photon. And so here's experimental results: coincidence rate versus delay time between photon detection events. So for two color centers now with indistinguishable emission, you get a drop of the coincidence rates close to 0. So actually the contrast of these G2 function measurements give you a measure of the indistinguishability. In this case, it was about 72%. So the photon emitted now by different atoms without any tuning is overlapping within, with high fidelity, and that's for solid state system where you usually do have a disorder and atoms are not always the same. This is, I think, quite remarkable property. So the system sort of is very stable in terms that owing to a higher symmetry of these color centers, they are not get perturbed by local electric fields. Yes?
It seems from what you say that the electric field seems to be the main mechanism for the disturbance, but basically these phonons are essentially not creating electric fields because they are, it's in carbon, so carbon is not a polar material. But you still see this huge phonon band that is suppressed when you do that. So is it really electrical, the mechanism
for the phonons, you mean? So there are two different mechanisms. One is related to static line shift between different color centers, and that's related to strain in the material, sort of. So, and the phonon sideband occurs because when exciting the atom from ground to the excited state, you not only excite the electron, but electron wave function basically changes and it gets kicked to the carbon nearby. So that creates a vibration of the lattice, and that's basically lead to absorption with creation of the phonon or emission with the creation of the phonon. And this is a phonon sideband. So those are two different features. The second can be, to be completely suppressed is relatively hard. There is still about 30% of emission in this with creation or emission of the phonons. All right. So now about the energy structure in more details of these defects. So we have seen pretty remarkable optical properties. But for making interface with atomic system having a long coherence time, we actually need spin structure in a ground state. So, so this is what happens for the Silicon-vacancy center. So the ground and excited states do have an interesting long-living sublevels in the ground state, but the energy level structure is pretty complex. So first of all, it do have orbital degrees of freedom. So there is orbital doublet in both ground and excited states, and the orbital states of silicon vacancy centers in a ground state are separated by about 50 gigahertz. So 50 gigahertz is correspond to a temperature of about a couple of kelvins. So the phonons are inducing dynamics between orbital sublevels of this ground state. And you can control the ground state sublevels by optical pumping. You can polarize and measure how much population was left in one of these sublevels in the ground state, and measure what is a lifetime at a few Kelvin temperature. And it turns out that the lifetime is pretty short. So at about 40 nanoseconds, the relaxation time of the orbital sublevel of this ground state at cryogenic temperature at around 4 Kelvin. So it's not very long, and perhaps not very interesting for storing the quantum state of light. There is also a richer, actually, or a level structure if you apply to your color center magnetic field. So every orbital state is also carrying a spin state, which is longer living. So if you place your sample, for example, on a permanent magnet and measure fluorescence spectrum, fluorescence excitation spectra, you will see the splitting of the line of individual atoms, individual impurity centers, and the splitting corresponds to appearance of the Zeeman shift associated with the spin sublevels. You again can control the state of individual atoms by making optical pumping cycle, placing all the population in one of the spin sublevels, and now look how long the spin state lives. So it's now a spin state, not the orbital state, and the decay time is significantly longer. So it's a millisecond time scale essentially as a decay at 4 Kelvin. So not every flip of the orbital lead to the flip of the spin state. So the spin state are living longer, and so this kind of create already now interesting system, because the spin state are significantly longer living than the orbital state, a millisecond.
How is that compared to NV?
NV center at this temperature have a relaxation time of tens of seconds, but it's it's just a relaxation times at the moment. Yeah, so the relaxation time here is faster. Yeah, but milliseconds is relatively long. So if you think about quantum repeaters, so that light within milliseconds can travel many kilometers. So it can be already interesting to distribute entanglement over a long distance.
So this is just the T1.
That's just T1 exactly. So this is not the full story. So T1 is just the classic lifetime of the classical state, but you want to have a lifetime of superposition of the state T2 time, which actually matter. And so to look at this, you need to basically control coherence in the ground state. That can be done, for example, by tuning pump and prop laser in resonance with a 3-level system where 2 ground states are spin states, and the excited states, it's the optical excited state. If you change the frequency of the probe and going through resonance, you will see the normal absorption profile, but also dark resonance. This dark resonance is related to creation of the dark state in the ground state, and the line width of this resonance is giving you a T2 star, so coherence time associated with the spin state. In this case, at 4 Kelvin temperature, it is about 4 megahertz, corresponding to a few hundreds of nanosecond T2 time. So not very long, not very long. So now how does compare to NV center? For NV center, that might reach some milliseconds. And so it seems to be not very promising. In this respect, so we have very good optical properties, but the spin state of this defect is still at 4 Kelvin, not good enough for storing the state of the photon for a long time. However, we also understand where the challenge is. So the challenge here is that the orbital state of defects are fluctuating at 4 Kelvin relatively fast. And the way to fight it in a very direct way is actually lower the temperature of experiments to a situation where KT is much smaller than the energy gap between 2 orbital states. So this is now 2 orbital state of the defect. This is 50 gigahertz, about 2 Kelvin. So if you come to a millikelvin temperature, everything freezes in a lowest energy orbital state, and now your spin state are not get affected by the relaxation between orbital spin sublevels. And so experiments of this type, why perform it? The first one in Harvard at about few hundred millikelvin temperature, where optical microscope was placed in a dilution refrigerator. And so there is quite a significant, basically, improvement of the spin properties of these defects. So I show you a few highlights. One is the ability to read out the spin state of a single atom by shining a resonant laser, because the spin state is now so long-living that you can start to detect the quantum jumps, or you can distinguish in a single shot manner two different spin state of the atom. So in a photon count distribution, if you measure the scattered photons, you get now two peaks. One is when atom is out of resonance, so it's essentially 0 photon counts. The other is atom is in resonance. So in this case, it was about 5 photon counts per readout cycle. So you can distinguish these two photon counting distributions. That means you can get access to a spin state in a single shot without averaging. So this is again not yet T2 time. So to measure T2 time, you have to get a coherent control. In this particular case, it was not done with sending two lasers, but by applying a microwave directly to a spin state. And at millikelvin temperature, so it's not very straightforward experiments. Usually, if you want to rotate spin, you want to rotate it fast, you send the very high power microwave pulses. If you're at millikelvin temperature, so you don't want to put too much power to dissipate, so you need to design your microwave structure in a good way. So this is a waveguide that was designed and fabricated. The microwaves are going here through. The wires are pretty thin, so about 5 micron. And so if you zoom in here, it's a picture of the ground and a signal wire with a single atom here sitting near the microwave wire, very, very close. That per milliwatt of microwave power, you get significant B1 field to rotate the spin. So now with this design in place, so you can send microwave pulses and rotate your atomic spin and then measure it optically. This is the result of this experiment, where rotation pulse, the resonance microwave pulse was varying in time, and now you see the Rabi oscillations of the cylindrical electron spin with high contrast, which don't show any significant decay. So on a microsecond time scale. So it's already longer than I was mentioning before. We don't see any decay. Now we can also define some pulse lengths that create superposition of this state, and so basically do very conventional electron or nuclear magnetic resonance experiments with these microwave pulses controlling the spin state. And one of them is very classical experiments in magnetic resonance to measure the coherence time is spin echo. So you initialize your spin state, the state of the atom, with a laser pulse. You apply a sandwich of pi half pulses separated by a train of pi pulses, refocusing some environmental fluctuations. So this is the result, the echo amplitude. It's the fidelity of the state you recover after your echo as a function of the delay time. And so with a significant number of pi pulses where it decouples well, you can reach millisecond coherence time at this temperature of a few hundreds of millikelvin. So lowering the temperature allows you actually to reach very significant coherence time for this defect, and having basically combining now good optical access to individual atoms with long coherence time of the spin state in the ground state. All right. So maybe just continuing the story in engineering of defects, I have to say that silicon is not the only element you can put into these splitted vacancy structures, but also germanium and tin actually are exhibiting very similar properties. So for germanium and tin, both have similar electron level structures. They can be introduced in a very similar manner. And here I show what happens if you implant germanium into diamond, where, well, it's a very similar emission spectrum. Just the zero photon line is shifted from 737 nanometer near infrared to the visible range around 600 nanometers. And these defects can be also introduced not only in a big diamond, but also in micro and nano diamond form. This is nano diamonds from Novosibirsk, where these germanium vacancy centers have been incorporated, and having a nano diamond phase might allow you to easier interface your diamond defects with external resonator. So this is something one can consider. Maybe one more point about the coupling of light and atoms. Usually you think that you need a high quality optical resonator, but if you have a very strong atom at hand, like one of those defects with very strong zero photon line, you can just focus your incoming beam and measure the scattered or absorbed photon, and it turns out that for good optical emitters you can actually measure the shadow or reflection even from a single atom without any cavity. So here's a picture of a single germanium vacancy center just in a free space sort of optics. So here's a normal kind of typical experiment where you measure fluorescence and cut the scattered light, and in solid state usually you have a lot of reflections. You usually need to cut this light to see the atoms. But it turns out that for these atoms, they're scattering so efficiently that it's enough just to send some picowatts of laser power, a few hundreds of thousand photons in to get reflection. And this is kind of a reflection picture of the atom. So the same frequency you get now, like this dispersive profile, that's happened because the photon reflected from the surface of the diamond get interfered with a coherently scattered photon from the atom. And so this contrast here, which can be like a few percent, up to 10% in a free space, is now related to coherent part of the interaction of atom and the light. All right, so maybe in the last maybe 10-15 minutes, I would like to show you one experiment. Yeah. Mm-hmm.
So if you compare the coherence times in silicon and germanium, so how do they behave?
So experiments in millikelvin have not been yet done for germanium. So in a sense, so I think it's difficult question to answer at the moment, but from the energy level structure and all the photophysics, so both defects are very similar. So we also for germanium vacancy center, we would expect by cooling it to a few hundred millikelvin to freeze the orbital dynamics and reach the milliseconds or longer coherence time. Mm-hmm.
Is it fair to say that if you put a heavier atom close to the vacancy, to basically shift down the phonon frequencies and make the defect more sensitive to phonons, or whereas if you put a light atom, so basically the phonons are going to cause high temperatures in the
I think the effect is not related to the size of the atom, but to the symmetry of the wave function. So it's more that if you have an atom which is too big to sit at the vacancy position for this particular defect family, so it gets shifted to position between two vacancy. Basically, this is a relaxed configuration, and this higher symmetry atom is getting less perturbing when for environment when you excite it into excited state. Mm-hmm. So that's sort of my understanding of this. Mm-hmm. All right. So I just mentioned that a single atom can absorb single photon or scatter single photon in a relatively efficient way, even without optical resonator. But it's still, it don't really get every photon absorbed. So it's at the moment it's still better to introduce atom into optical resonator. And I would like to show you now an experiment that was performed using an atom, the silicon-vacancy atom, placed between two Bragg mirrors in a waveguide. And It's a collaboration with Lonker and Lukin group in Harvard, and the idea here is basically to control the scattering of light in a waveguide by atom and get control over transmission of the waveguide by inner state of the single atom, single silicon vacancy defect. So this device having long-living spin state can also allow you to make this kind of interface where you map the state of the photon into atom and retrieve it back. The waveguides and resonators that we have been using are monolithic diamond resonators that are not like external cavities. So the whole device has been done in diamond by etching material. So this is a freestanding diamond beams where etching was used to create a beam itself, and focused ion beam was used to create these holes, making Bragg reflectors. So you have two of these mirrors, and in the center you have a hot spot where you implant your NV center. The Q factor of this resonator is experimentally measured in a visible range, was reaching about 7,000. So it's not very high Q factor if you compare it with the large fabric cavities, but the mode volume of the resonator is very small. It's on the order of lambda over n, providing you a very high electric field per photon. So photons are very confined here. So the finesse is hard, for me, like hard to define, because this, the resonator is so small that I think that the second mode is out of range. So it do have just one mode. It's the area here is it's I think below a lambda between yeah. Finesse is hard to So Q factor is a good. So the defects have been implanted in the hotspots. And so this is now a picture of two devices with silicon-vacancy center inside. And you can now measure basically interaction of light and matter in such a waveguides by inserting or injecting light on the left side of, and then basically collecting the light through your resonator. You also have additional channel just to control the fluorescence of silicon vacancy. You also can measure in a emission in a free space. And the transmission measurements through a resonator are shown here in a blue line. So it's basically the width of this resonance is your Q factor. So in this case, it's or defined by Q factor. The width of the resonator is about 80 gigahertz. And on top of this relatively broad resonator transmission spectrum, you get very sharp mean. and create the material where you have very high density of color centers. It can be D centers or silicon-vacancy centers. So this is a picture of diamonds generated in or grown in Tsukuba in Japan, where you have very high concentration of color and V color centers on the order of 50 parts per million. So in such a material, the distance between individual atoms gets so short that there is a significant dipole interaction, and in both sense, in both sides. So optical dipole interaction, electrical dipole of different color centers, but also magnetic dipole interaction. And the physics that we have heard here during the workshop of magnetically coupled atoms that we have discussed in terms of atomic system can be translated now to a solid state material where you can control, polarize all these color centers, bring all these things in the well-defined initial state, and then see the evolution under desired Hamiltonian. And you also can potentially control the strength of the coupling between atoms by using dynamical decoupling techniques. So I think this is interesting avenues towards many body physics that this solid state system allows you. And I think with this I conclude and would like to thank you for your attention.